I'm trying to solve actually for the radius of the circle. I'm trying to find what's the minimum value of f. And second, at that value of f, actually the value at that point, the value of f and the value of g are not equal. Right? G is equal to 3 because I'm on the hyperbola xy equals 3. The value of f will be the square of the distance, whatever that is. I think it will end up being 6, but we'll see. Okay, so you can't really set them equal because you don't know what f is equal to in advance. Yes?
The theory behind this procedure that we're translating the problem of finding a minimum or maximum into trying to find the closest distance to a point.
Not quite. No, we are not. So, I mean, actually, here I'm just using this idea of, finding a point closest to the origin to illustrate an example of a min-max problem. The general problem we're trying to solve is minimize f subject to g equals constant. And what we're going to do for that is we're really going to say instead, let's look at places where gradient f and gradient g are parallel to each other and solve for equations of that. I think we completely lose the notion of closest point if we just look at these equations. They don't really say anything about closest points anymore. Of course, that's what they mean in the end. But in the general setting, there's no closest point involved anymore. Does that? Okay. Yes? Yes, so it's always going to be the case that at the minimum or at the maximum of a function subject to a constraint, the level curves of f and the level curves of g will be tangent to each other. So that's the basis for this method. Okay, so I'm going to justify that soon. So, yes, it could be minimum or maximum. Or in 3 dimensions, it could even be a saddle point. And in fact, I should say in advance, this method will not tell us whether it's a minimum or a maximum. We don't have any way of knowing except for testing values. We can't use second derivative tests or anything like that. Okay, I'll get back to that. Yes?
Why can't you just set y equals 3 over x?
Yes, here you can set y equals to 3 over x, and then you can minimize x squared plus 9 over x squared. In general, if I'm trying to solve a more complicated problem, I might not be able to solve. Okay, so I'm doing an example where, indeed, here you could solve and remove one variable, but you can't always do that. And this method will still work. The other one won't. Okay? I don't see any other questions. Are there any other questions? No? Okay, then I see a lot of you suddenly stretching and so on, so it's very confusing for me. But okay. So how do we solve these equations? Well, the answer is, in general, we might be in deep trouble. Okay? There's no general method for solving the equations that you get from this method. You just have to think about them. And so, sometimes it will be very easy. Sometimes it will be so hard that you can't actually do it without a computer. Sometimes it will be just hard enough to be on part B of this week's problem set. Okay. So in this case, I claim in this case we can actually do it without so much trouble. Okay? Because actually we can think of this as a 2x2 linear system in x and y. Well, let me do something. Okay? So let me rewrite the first two equations as 2x minus lambda y equals 0 and lambda x minus 2y equals 0. Okay, and xy equals 3. Right? That's what we want to solve. Well, I can put this into matrix form. 2 minus lambda, lambda minus 2 times xy equals 0. Now, how do I solve a linear system, matrix times xy equals 0? Well, I always have an obvious solution. Okay, x and y both equal to 0. Is that a good solution? No, because 0 times 0 is not free. Okay? So we want another solution. So the trivial solution, 0, 0, does not solve the constraint equation xy equals 3. So we want another solution. When do we have another solution? Well, when the determinant of the matrix is 0. Okay? So we have other solutions exist only if the determinant of the matrix is 0 and where M is this guy. Okay? So let's compute the determinant. Well, that seems to be negative 4 plus lambda squared. So that's 0 exactly when lambda squared equals 4, which is lambda is plus or minus 2. Okay? So already you see here it's at a level of difficulty that's a little bit much for an exam, but perfectly fine for a problem set or for a beautiful lecture like this one. Okay? So how do we deal with, well, we have two cases to look at, lambda equals 2 or lambda equals minus 2. Let's start with lambda equals 2. If I set lambda equals 2, what does this equation become? Well, it becomes x equals y. This one becomes y equals x. Well, they seem to be the same, okay? X equals y. And then the equation xy equals 3 becomes, well, x squared equals 3. So I have two solutions. One is x equals root 3, and therefore y equals root 3 as well, or negative root 3, negative root 3. Okay? Let's look at the other case. Well, if I set lambda equal to negative 2, then I get 2x equals negative 2y. That means x equals negative y. The second one, 2y equals negative 2x, that's y equals negative x. Well, that's the same thing. And xy equals 3 becomes, well, negative x squared equals 3. Can we solve that? No. Okay, so there's no solutions here. So now we have two candidate points, which are these 2 points, root 3, or negative root 3, negative root 3. Okay, so let's actually look at what we have here. Well, maybe you can't read the coordinates, but actually the point that I have here is indeed root 3. And how do we see that lambda equals 2? Well, if you look at this picture, the gradient of f, that's the blue vector,